Okay. All right, we're going to talk about surface integrals now. This is where we are integrating over a surface, okay? So the surface S has a vector equation R of u and v, where x, this is the vector equation, x of u and v, y of u, oh my goodness, y of u and v, your j, and z of u and v is your k component. And the ordered pairs u and v are in a region D. All right, the surface has this vector equation. If we want to integrate over the surface, the double integral of the surface area of a function x, y, z ds is going to be converted to a double region over the integral D, f of r of uv times the magnitude of r with respect to u crossed with r with respect to v dA. I'm sorry, I got all scrunched in there together. Of course, there's a more detailed representation of all this where you divide this into little regions and it's the Riemann sum and all that. But can you read that?
Just the projector of the one.
Oh, okay. All right, so let me show you what I mean. Problem 6. They want us to find the double region, means double integral of the function xyz ds over S, which is a cone with parametric representations. X is u cosine v, y is u sine v, and z is u. And u ranges from 0 to 1, and v ranges from 0 to pi over 2. All right, this is the parametric representation of S. This is your R of uv, okay? So R of uv is the vector equation u cosine v, u sine v, and u. So that's what your R of v is, R of u and v is. So if you're going to do the surface integral of this, you need to take the derivatives. You need R with respect to u. So the derivative with respect to u is going to be the cosine of v, the sine of v, and 1. You need R with respect to v. The derivative of cosine is negative sine of v. The derivative of sine is the cosine, and the derivative of u is 0. Okay, y'all following me? All right, then for my formula, I need to do the cross product of these two. So ijk cosine v sine v1 negative u sine v u cosine v 0. All right, so this is I 0 minus u cosine v minus j 0 minus a minus makes that u sine v plus k And that is going to be u cosine squared of v minus a minus, which is plus u sine squared of v. So this is the vector negative u cosine of v, negative u sine of v, and this one, if I factor out a u and put cosine squared plus sine squared, that's 1. So that's going to simplify to u. Okay, Devin, we're taking a surface integral. Surface integral where the surface has got this vector function, and this is the formula we're using. So this is our problem. This is problem number 6, actually, from your book. So this is my integral. This is my surface here that I'm integrating over. So I have to do the partial with respect to u, partial with respect to v, then do their cross product. And now I'm going to have to take the magnitude of this thing. Okay, so that's sort of briefly where we are. All right, so now the magnitude of this thing is the square root of, what's going to be what, u squared cosine squared plus u squared sine squared plus u squared. If I factor u squared from here, that's going to give me cosine squared plus sine squared plus u squared. This is 1, so u squared plus u squared, that's 2u squared. So that looks like u square root of 2. Okay, everybody with me? Okay, so when I do my integral, my double integral up here, I have to have f of r of u and v. That means I have to substitute for x, y, and z. I've got to substitute these parametric equations. All right, so putting all of that in here, I'm going to have, these are my limits of integration. Again, they were given to me. So I guess 0 to 1 and 0 to pi over 2. My x is u cosine of v. My y is u sine of v. My z is u, and then I also have this other u square root of 2. This is dv. This is du. And you integrate all of that. Probably could simplify a little bit. Square root of 2 can come out. U times u is u squared. Oops, no, it's u to the 4th. 1, 2, 3, 4. U to the 4th. Cosine v, sine v. dv, du. And Tori's doing that for us, but whatever that is. You have what expectations? Oh. Well, we should. Square root of 2 times integral. What did you get? That's what I got. I know, that just looked like, that's a weird number. I just thought it looked weird.
Well,
Okay.
I was like, that was better. For 2 over 10.
That's what she and I both got for that one. Okay. All righty. Now this is,
I put it in before you simplified
Oh, okay. It must be right then.
There you go.
Okay, like that positive attitude.
Have to be.
All right, now, if your surface is given as a function of x and y, so if your surface, we're still doing surface area, and this is if your surface is expressed as a vector equation. If your surface S has the equation z that is equal to x and y, then instead of the parametric equations being x, y, and z, the parametric equations are x equal to x, y is equal to y, and z is the function of x and y. So then the formula, the double integral formula of f of x, y, z ds is the double integral over the region D of f of x, y, g of x, y. In other words, you replace the z, make it in terms of x and y, times the square root of the partial of z with respect to x squared plus the partial of z with respect to y squared plus 1 dA. So this is comparable to the vector function. All right, and I'll work one like that. Number 9 wants us to do the surface of x squared yz ds. So it's a surface integral. S is the part of the plane where z is 1 plus 2x plus 3y that lies above the rectangle 0 to 3 and 0 to 2. Now remember, when they write this, this just means that x goes from 0 to 3, and this one means that y ranges from 0 to 2. So this is your x's and your y's. All right, so when your surface is written in as a function of x and y, like this is, then you would use this one. So you need the partial of z with respect to x, which is 2, the partial of z with respect to y, which is 3, and then you need the square root, this part right here. You need 3 squared plus 2 squared plus 1. 9 plus 4 plus 1, which looks like it's the square root of 14. Okay. Then they gave us our limits of integration right here. And we know that this is the second part of this formula right here. So now we just need to make sure we have x, y, and we need to replace that z with that right there, because you've got to have all x's. You can only have 2 variables when you're all said and done, because you only have 2 integrals. So you're integrating, let's do 0 to 3 on the outside, 0 to 2 on the inside. You have x squared y. Then your z is 1 plus 2x plus 3y. Don't forget your square root of 14. And this one is dy, and this is dx. And that's how you set up that surface integral.
And then just stick it in your calculator.
Then just put it in your calculator.
Now, does it matter, doesn't matter which one you first you do
No.
as your integral?
No, it doesn't matter, because these are both constant, so it doesn't matter if you do your x's first or your y's.
Okay.
Just make sure you
Put them
put the correct ones with the
in
correct.
right order.
Right. Okay. Are we okay on these surface integrals? Okay, what did you get? 171 square root of 14. Okay, that looks like a nice answer.
That's got to be
There's the square root of 14, so it's got to be right. Okay. All right, everybody okay with this? Because we're fixing to switch gears and now to do the surface integral over a vector field.
I think that's 16.
No, it's still at 16.7.
Oh.
We're just still in the same thing. All right, but we're doing surface area now over a vector field, and we need to talk about an oriented surface in order to be able to do this. Oriented surface. All right, an oriented surface, and we're talking about a surface that's got two sides to it, which sounds strange, right? You think, well, every surface has got two sides. But there's a surface, and this is one of them, my little handy decoration here that can't show on that thing. This surface actually has one side to it. This is called a Mobius strip. And this is a one-sided surface. It started off as two sides because it was just a piece of paper that I cut and twisted and put together. But once I put it together in this configuration, it makes one surface. And I will show you why that is true. And I meant, maybe it'll do better with this. And I'll try to do it on the screen so maybe they can see it. If I take, I'll just take a dot right here. I know. If I put my pencil right there and I don't pick it up, whoops. This is not going well. I'm going to get right back to where I started. Whoops. I didn't pick it up. Pretend like I didn't pick it up. I'm going to be right there. Ah! La, 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 la. Poof. I got right back where I started. Of course, it would have been better if I hadn't had to try to put it under that screen. But anyway, this is a one-sided surface. And I cannot do a surface integral over a one-sided surface because a surface integral involves normal vectors that point in this. To get an oriented surface, you have to have normal vectors that kind of point in the same direction, if you will. All right, let me just put this down for a second. This is my surface. A normal vector, you know, is a perpendicular vector, okay? So if I found a perpendicular vector to this surface right here, it's kind of pointing up. But as I travel around the surface, this vector is no longer pointing up. This surface is pointing out this way. I'm still on this surface, and when I get to the inside, well, what I say the inside, it's not the inside because I'm still on the same surface. Now I've got vectors that are pointing this direction. These vectors are not all pointing the same direction, so I can't orient my surface. Okay? We have to have a two-sided surface so that you're only talking about two normal vectors that point in two different directions. A normal vector, this is a two-sided surface. All right? Normal vector, there are two of them. Normal vectors on the top are going to point like this. Normal vectors on the bottom are going to do like this. Right? There's only two. I can orient this. If it's pointing up, we usually say this is a positive orientation. If the vectors point down, this is a negative orientation. So we can orient a surface like this. So we can take an integral over a surface that can be oriented. So that's the idea. And that's a very brief layman's definition of an oriented surface, okay? But that's kind of the idea here. Okay, so if you have an oriented surface, let me find the top of marker. And we also need a closed surface. Closed surface is like a sphere. Okay, so that would be a closed surface, okay, all the way around. So if we do the surface integral over an oriented surface that is positively oriented, or pay attention to the positively oriented, if S is given by the vector function R of u and v again, then the surface integral of, I'll write this down, surface integral of F, which is a vector field, over S, is given by F dot dr, which can be changed to the double integral over the region D of F dotted with RU crossed with RV, dA. This is if S is given as a vector function. I'm going to go ahead and give you the other one too. If S is given as a function of y, of x and y, you're still integrating over a vector field. And if the vector field F can be written Pi hat Qj hat plus R K hat, then you can evaluate this double integral over the region D of negative P times the partial of G with respect to X minus Q times the partial of G with respect to Y plus R dA. And this is for a positively oriented surface. If the surface is negatively oriented, multiply it by -1. If it is not positive orientation. Okay, so let me tell you this too. Say if you have a sphere or anything, ellipsoid or something like that, if they say the orientation is toward the origin, that's down, that's negative orientation. For that to be a positive orientation, it needs to be oriented away, going away from the origin. Okay, kind of out. So usually if it's in, it's a negative orientation. If it's out, it's a positive orientation. Okay. Now I will work a couple of problems like this. Number 22. Actually, oh, by the way, this is also called the flux. Do y'all do flux in physics? All right, this is also, is that why it looked familiar? Which one of these do y'all use? This one or this one? This one? This one? Okay. It's the flux. So y'all ought to be good at that. All right. Number 22 says f of xyz is z y j. Sorry, that's a j. X k hat, and it says S, the surface S is the helicoid of exercise 7 with an upward orientation. So let me get back to exercise 7. All right, this is vector equation R of UV, U cosine V, U sine V, and V. U goes from 0 to 1, and V is going from 0 to pi. Okay, since they gave me S in terms of a vector function, I'm going to go back up and use this one right here. So I need partial with respect to u, partial with respect to v, and then their cross product. So r with respect to u, sine v, sine v, 0. R with respect to v, oops, negative u sine v. Partial with respect to v is u cosine v, and that's a 1. Then I need jk. So cosine v, sine v, 0, negative u sine v, u cosine v, and 1. Sine of v, j, cosine v, k, is u cosine squared plus u sine squared. So this is going to give me the vector, the sine of v, negative cosine of v, and that's a u. Okay. Wait till I get here. All right, my f function up here. I'm going to have to, by this formula, excuse me, I've got to take the dot product of two vectors. Well, I have the vector, I have this vector. I need this written as a vector. So, and I need it in u's and v's. So f written in terms of the parameters, z is v, so that's there. The y is u sine v, and x is u cosine v. So when I do my double integral, 0 to 1, 0 to pi, I'm taking the vector v u sine v, u cosine v. I'm going to dot it with that cross product. This is dv, this is du. And y'all remember how to do a dot product? Before you can put it in your calculators, you need to do that. So that would be v sine v minus u sine v cosine v plus u squared cosine v, then dv du. And then you can put that in your calculators for your surface interval. If I multiply right, that times that, plus that times that, and that. And I don't know what this one is either. I got pi. Y'all expected something a lot more complicated, didn't you? You didn't get pi? Make sure you put your times symbol when you're multiplying stuff. Well, if you have U's and V's, make sure you put du dv. Okay, then I was going to do one last problem where your surface is given in terms of x and y instead of as a vector function. And number 26 is one like that. The vector field is yi minus xj plus 2zk. S is the hemisphere, x squared plus y squared plus z squared equals to 4, where z is greater than or equal to 0. And it is oriented downwards. So I can tell you right now it's oriented downwards, so that's a negative orientation. We're going to have to multiply -1 times our integral and -1 times our answer when we're finished. So just don't forget that part. All right, I am going to solve this for z. And since z is greater than or equal to 0, I'm going to look at the positive square root. So z is the square root of 4 minus x squared minus y squared. Now, if you'll look back at the formula that you're using for this one, it's this one. And this z, that is your function g. This is g of xy. So you need the partial of this function with respect to x, and you need the partial of this with respect to y to put it in this formula. Okay? So g with respect to x, 1/2 4 minus x squared minus y squared to the -1/2 times the inside, which is -2x, which makes that -x over the square root of 4 minus x squared minus y squared. All right, the partial with respect to y is going to be just like that, except with respect to y. So that's -y over the square root 4 minus x squared minus y squared. Okay. This also uses P, Q, and R. Up here, this is P, this is Q, this is R. So P is Y, Q is -x, and R is 2z. But what is z? So r is actually 2 times the square root of 4 minus x squared minus y squared. That's r. Now, Is everybody with me so far? I'm just getting the pieces, parts that I need. I've got my PQR. I've got partial with respect to x, partial with respect to y. I need my limits of integration. Limits of integration are going to be projected down to my xy axis because everything's in terms of x and y. So if I go back up here and project this down to my xy axis, or my xy plane, to my xy plane, that is going to give me x squared plus y squared is equal to 4. Circle with a radius of 2. So I am changing this to polar coordinates to get my limits of integration because it is circular. So if I change it to polar coordinates, my r is ranging from 0 to 2. My theta is going 0 to 2 pi. So when you change everything to polar coordinates, you've got to get rid of your x's and y's, and you have to add an extra r in your problem because you're changing to polar coordinates, remember? Okay. So, y is, if I put polar coordinates, y is r, which one is this one? Isn't it r sine theta? Negative x is going to be negative r cosine theta. And this is going to be 4 minus r squared. Because x squared plus y squared is r squared. And over here, your partials, when you change them, partial with respect to x is going to be negative x, which is negative r cosine theta over the square root of 4 minus r squared. Partial with respect to y is negative r sine theta over the square root of 4 minus r squared. I think it's going to all simplify a lot, so at least I hope it does. All right, so limits of integration 0 to 2, 0 to 2 pi. I have negative p, so that's negative r sine theta, multiplied times the partial of g with respect to x, which is negative r cosine theta over the square root of 4 minus r squared. Minus, let's see, minus q, where's q? Minus a minus is going to make that plus r cosine theta, so partial with respect to y, plus my r, which is this, 2 square roots of 4 minus r squared, and I'm running out of room. I need an extra r in this problem, and then I need my d theta and my dr. Okay, all this is supposed to be multiplied times that. Now if I look at this, that's positive r squared sine cosine, that's negative r squared. These two terms are going to zero out because they're exactly alike. So that and that zero out. 0 to 2, 0 to 2 pi. And I'm integrating 2 square roots of 4 minus r squared times my extra r, d theta, dr. And that turned out not to be quite so bad. I had 32 pi over 3, but, right, this was a downward orientation, so my answer is negative 32 pi over 3. Because the orientation is downward, I multiply by -1. I could have multiplied by -1 when I set up my integral, but I just saved it to the end. Just don't forget it, whatever you do. Alrighty. What questions do you have about these surface intervals?